Imagine a steel transmission shaft rolling off the line. You grab a pair of calipers, check the diameter, and it is perfectly within tolerance. But when you load it into a machine and spin it up to 3,000 RPM, the entire assembly violently shakes. The calipers only confirmed the distance between two opposing points on the surface. They completely missed the fact that the actual center line running down the length of the shaft is bowed like a banana. To close the gap between a static size measurement and the physical shape of a part, engineers rely on a specific geometric dimensioning and tolerancing tool, Straightness. Relying strictly on size measurements creates a false sense of security. Form controls are required to ensure the part's actual geometry allows for the clearance and movement required in a dynamic assembly. Straightness is an independent form control. It evaluates a feature strictly against itself. Because it ignores how the feature relates to the rest of the part, datum references are completely forbidden in this feature control frame. When controlling the exterior of a part, the drafting syntax is highly specific. The leader line extending from the feature control frame must terminate directly on the surface profile line of the drawing. This creates a two-dimensional tolerance zone. The true surface of the manufactured part will always be slightly jagged. Every individual line element along that surface must fall entirely between these two perfectly straight parallel boundaries. This application is hyperlocal. It only guarantees that the outer skin of the part is flat along one isolated line. It ignores the overall mass, the thickness, and how the component will fit into an assembly. To dictate how a component actually interacts with mating parts, we have to look past the surface skin and regulate the internal skeleton, what GD&T classifies as a feature of size. Controlling the axis requires a syntax shift. The feature control frame must be attached directly to the size dimension, and a diameter symbol is placed inside the frame to define the shape of the tolerance. This illustration shows the new boundary. We are no longer looking at a 2D slice. The tolerance is a three-dimensional mathematical cylinder, and the part's jagged, derived median line must sit completely inside it. Standard engineering drawings are governed by rule number 1, the envelope principle. This rule dictates that if a part is produced at its maximum material condition, its thickest allowable size, it must default to having perfectly straight form. Applying an explicit axis straightness callout introduces a deliberate exception. It overrides rule number 1, legally allowing the part's central axis to bend beyond that standard envelope of perfect form. Without this specific override, machinists would be forced to hit perfectly straight form on every heavy feature they produce. This wastes money and machining time on parts that functionally do not require strict straightness to operate. To translate this axis tolerance onto the shop floor, engineers add a circle M modifier into the feature control frame. This stands for maximum material condition. For an external feature like a pin, this modifier creates a virtual condition. You calculate it by taking the maximum material condition size and adding the straightness tolerance. This math converts directly into the interior diameter of a physical tool. That tool is a physical go gauge. An inspector takes this precisely machined steel sleeve and slides it over the manufactured shaft to instantly verify if the part will fit into its final assembly. If that modifier is left off the drawing, the part has to be inspected on a coordinate measuring machine. An operator must scan multiple cross-sections and run algorithms just to calculate where the derived median line actually sits in space. Adding the maximum material condition modifier turns an abstract engineering requirement into a practical shop floor inspection, replacing slow software analysis with a physical check that takes seconds. Take a look at this dual callout on a stepped shaft. Based on the rules we've established, which of these two specific controls dictates the median line and allows for a go gauge inspection? It's the callout placed on the dimension. Placing the frame there targets the internal axis, and adding the circle M modifier changes the physical inspection requirement to allow the hard go gauge. Dragging a leader line to a surface profile versus snapping it under a dimension takes the same amount of effort in CAD. Yet that choice determines whether the factory uses a high-speed manual gauge or a precision CMM for every part produced. Axis straightness is clear call for long components. If a drive shaft must pass through multiple bearing journals, controlling the bend of that axis prevents the shaft from binding as it spins. This cheat sheet tracks the most common drafting errors. The fastest way to break a drawing is incorrectly adding a datum reference to a form control. Straightness only checks a feature against itself, so datums are invalid. The next error is confusing the leader placement. A leader pointing at the surface controls the 2D skin. A frame attached to the dimension controls the 3D skeleton. Next, ensure you are not using the 2D straightness line when the part requires the 3D flatness parallelogram. Finally, never apply a material modifier unless your specific functional intent is a clearance fit. Straightness takes strict size dimensions and ensures they actually function in motion, but straightness only applies to single lines and cylinders. To control massive, wide surfaces, we have to scale this logic into 3 dimensions.